Okay, fire a projectile, it goes up an incline. That's a pretty complicated situation, okay? So we want to talk a little bit about how this works, just to expand your idea of projectile motion. It comes down to, you need the equation of motion in a coordinate system. So what we're going to do is, we're going to say, okay, here's your coordinate system. And this incline is at some angle. I think it's probably good. I'm going to call that angle alpha. I don't think that's what the book calls it. I don't want to use the same thing they do. Okay? Alpha is a perfectly good angle. Theta is used a little more generally. You kind of sometimes want to avoid that if you're not certain. Although I tend to use theta quite a bit. Okay, so here's your path. Well, your path is very simple. We'll assume x naught equals y naught equals 0. Then the path is v naught x plus 1/2 ax t squared in the x direction. It's just your equation of motion in the x direction, right? Plus v naught y plus 1/2 ay t squared times your j vector. And that equals just plain old v naught xi because ax is 0. And for an ideal projectile. And I'll go ahead and substitute the 5 meters per second squared, although there are advantages to leaving this as AY. So you just work with the symbols and then plug the numbers in at the end, as your book and Open Math advises you to do. So there it is. There's your path. Your question is, when does this thing hit the incline? Well, you hit the incline when I'll call it XF. I'll have a good place to play, but I'll have to do this. You have some XF and some YF such that your YF over XF equals tangent of theta. That's when you're going to hit the incline, right? Okay, for any other point, you know, x over y is not equal to the tangent of theta, right? Okay, so solve y over x is tangent of theta. So this equals x of ti plus y of t j, and we could put y of t over x of t equals tangent of theta, tangent of alpha. You get a very simple equation. Okay, you're going to get and it's, I've got v naught x here. V naught x times 2. Looking at this equation, I suddenly discover I needed a t here. Well, tangent of alpha, if you're given the angle, is just a number you can calculate with a calculator, right? So what kind of an equation is this? Now, in terms of what you've done, this should be obvious. Okay, this is a quadratic equation. You'll know, assume, we know, v naught y, v naught x. We know the acceleration. We can easily solve this for t. Okay? If we want, we say we can solve this equation in symbols. Just a quadratic equation, use a quadratic formula. Keep your wits about you, it's not difficult. Okay? It's easy to lose your wits, and then it's difficult. Okay? So keep your wits about you if you can. Let's rearrange this into the form of at squared plus bt plus c equals 0, and plug into the quadratic formula, right? You're not likely to get something you can factor. The real world is not that cooperative. And if you did get something you could factor, there'd be uncertainty in it, so you really couldn't. So there's no point in even trying. Just rearrange this. So what looks like a really daunting situation really is not that bad. Because it's easy to get this, it's easy to get this if you have sufficient information. Once you see that this over this has to equal the tangent of theta for this thing to hit the incline, pretty much home free. Okay, very good.